Now, the objective today is to talk about hydraulic modeling, in particular using the software that we've had under development for 35 or 40 years to do hydraulic modeling. This software is primarily, our primary objective is to provide very comprehensive modeling capabilities for hydraulic and fluids engineers. So what I want to talk about at the first part is the graphical user interface, which is really the way that you will develop your models and edit models and provide data, and then some of the unique hydraulic capabilities. As I say, our goal has always been to provide a very wide range of hydraulic capabilities so the engineers can do the various tasks that they need to do with dealing with pipe systems, water distribution, sewage collection, chilled water, hot water, all these different things. The first part of this is talking about using the graphical user interface. What is a computer model? Putting backgrounds in the model, creating the model, providing data, and analyzing and looking at results. And I want to go over this fairly quickly. I hope there is a demo that you all could have downloaded or still can, and hopefully this will allow you to very quickly get up to speed on creating hydraulic models. Now, what is a computer model? Well, it's just a representation of a piping system that includes nodes and pipes. And this is a picture that shows a system with a pump and a tank and a bunch of pipes and junction nodes where the pipes connect. Each of the pipes will have some data associated with them, and each of the nodes will have some data associated with them. We can have a background map, and as shown here. So these are the key elements of your hydraulic model. What do you get from your hydraulic model? Well, in general, you run an analysis, you get pressures and flows. So you're seeing here, basically, we're getting a pressure at every junction. We're getting a flow in every pipe. And we can do this for any number of simulations or time periods. We can run just a series of simulations that are snapshots showing what's happening in the system. For example, if we had a pump on and we turned the pump off, we could see the pressures and flows with the pump off. If we increase the demands, we could see the pressure and flow with the demands increased. We can also do what we call extended period simulations, EPS, 24-hour simulations. And when we do that, we'll get histories of maybe the levels in the storage tanks, the pressures at various junctions, that sort of thing. And we don't have to do 24-hour simulations. You might be looking at how long it takes to load to fill a tank, and this simulation could be on the order of an hour or even minutes. And finally, there's transient simulations where we're looking at what happens when the power fails to a pump, and you get very fast transients. And these are very important because every system goes through periods of starting up and shutting down. So at this lower part, we may have a history of pressure at some point in the system, showing the high and low pressures. It may show that you form vapor cavities. All sorts of things can happen. So this is basically what you get out of your computer model, the hydraulics of the system. Just snapshot hydraulics, or hydraulics over extended periods of time, or hydraulics due to rapid transients. And we handle all three of these situations. If you had a hydraulic model, you could answer a question like this in just minutes. Could we add a new 6-inch line here, feeding a hospital that needs 500 gallons per minute? Now, of course, to answer that, you need to be able to do the hydraulics of the system. What pressure is going to be available where you connect the line, and under different conditions. So if you have the hydraulic model, you can very quickly add this segment of pipe to the model and run the analysis. So these are just an example of the advantage or the necessity of having hydraulic models available. So this is sort of what, how do we view a hydraulic model? The principal engineering tool is a computer program to do hydraulic analysis. In this case, for steady state, it's our KYPipe engine. For transient flow, it's our surge engine. But these are doing the hydraulic calculations, solving the energy equations and momentum equations for complex systems. But an equally important part of a model for users is the graphical user interface. And this is how you interact with to create models. And we've been developing an interface primarily for engineers to use to be able to quickly and easily generate models and modify them and provide data. This is the goal. We're not working inside AutoCAD or inside GIS. This is just to make it as simple and as easy to use as possible. We have a graphical user interface designed just for pipe system modeling. And how it works is shown down below. You can specify any number of conditions, how many pumps are on, which valves are open, what percent open are they. If you have a gate valve, you could have it 30% open or 90% open. What loads are in your system, what demands. That's what most of the piping systems are designed, is to provide flow. For example, a gasoline supply system for airplanes, that sort of thing, or just a water distribution. They supply flow to the users of the system. And so you specify what conditions you want to look at, and then the hydraulics is calculated using our engines and shows you how the system will operate. When we do engineering of piping systems, of course, we're concerned about maintaining the conditions that we want. In other words, delivering the flows at within a pressure range that's acceptable. We can't exceed the high pressures, and because we could burst pipes and ruin components, and we also have to maintain a certain minimum pressure to maintain the level of support, or the level that we need to maintain the system at. Now, the final comment on this page is that model elements can be georeferenced. They are. I mean, we have a model. It's associated with a very precise coordinate system, and you can use any coordinate system you want, including state plane or any type of coordinate system. So basically, you have your data georeferenced, which is a GIS representation of the data. Well, when you create a model, I want to talk about the steps that you go through using the Pipe 2000 GUI, which again we've simplified it to the point where there's just a couple very simple clicks of the mouse, and you can develop your models. Now, the list here, we can put backgrounds in, maps, grids, that sort of thing. We can lay out the pipe system, provide data, do the hydraulic calculations, and look at the results, look at the data, labeling your pipe system. That's one very huge advantage of doing things graphically, is that we can display the data and the results on the screen. Well, inserting a map, there's of course a button here to add backgrounds. You go to a browser. I don't want to get into the details, however, but in the browser you can access any number of background map files, raster files, vector files, bitmaps, DFX files, drawing files, any sort of thing. So there's a wide variety of types of background maps you can put in. And the next couple slides illustrate. Here's a background map of using the state of Kentucky's Department of Transportation highway maps. These are raster files, and you can go in and get great details here. These are scaled, and you can lay out piping, and the lengths of the pipes will be computed based on the scale of the map. Here's a DXF file of a subdivision. We have basically lots and piping going out, and we could put this in as a background map and just superimpose the piping according to how it appears on the DXF file. USGS maps are available. Raster files of the USGS topo maps are very, very useful. They have elevations. They have landmarks like buildings and so on, as shown in this map. So you can provide a very good background for your piping system if you have a USGS map of the area that your piping is being installed. And finally, here's a schematic. You don't have to do your systems to any sort of scale. If you had a schematic picture of a piping arrangement, you could import that as a JPEG file or a bitmap or any number of types of files, and you could lay out the piping based on what's in the schematic. So there's a wide variety of possibilities. In this case, it wouldn't be scaled normally if it's a schematic. So you wouldn't have the lengths being computed based on the scale. You would be inputting the lengths based on the dimensions of your piping system. You can put grids in. You can choose any grid size you want. This is showing some major grids that are 1,000 feet and some minor grids that are 100. You can customize that. In the Midwest, they often use mile grids because their roadways and so on are laid out on mile grids. So they use grids of 5,280 feet. So you have total flexibility here for putting grids in as a background. And you can put both grids and maps. And so you have a sort of a double set of background references. And so all these are options that you have when you're creating a piping system. Now, the actual creation of the piping system can be done in a simplified manner. We're saying it's a three-step process, or there's three operations. One, you left-click to select an existing node in your system or pipe. In other words, if you have a schematic, you want to provide data for a node, you just left-click on that node. When you're creating a model, the second item here is that if you're in the layout mode, which is how we create the models, if you have a selected node and you move the mouse and right-click, it adds a pipe section and a new node, and that's basically how we lay out systems. We go in and we just move the mouse and right-click, and we can lay out any arrangement that we want. And finally, of course, the system is composed, as I mentioned earlier, of nodes and pipes, and the nodes can be a variety of different elements: a junction, a pump, a tank, a regulator, a valve. There's all sorts of different types of nodes. And so the third item here is if you select a node, there's a drop-down, and you just select from a drop-down of about probably 15 different types of nodes. You select the one you want. Now, the next couple slides will sort of illustrate this in some detail. Here, for example, if I just want to start a system, I just go in and right-click. It will lay down a node. There's no selected node to start with, so when you just are starting your piping system, you just basically right-click, and you're in a layout mode. And now if you move your mouse to another location, and you right-click in that location, this is what happens. It adds a pipe section and a node. And now this is a selected node. And so if I move the mouse again and right-click, I can continue to lay out piping in any alignment that I want. So basically, that's all there is to it. So if I went along and laid out the system. Now, if I want to go back and, say, go off in a different direction, I can go back and select any node that I've already laid out, left-click to select it, and then I can move the mouse out and right-click, and I will start laying out piping from that location. So you can make any arrangement you want. Now, if you go and you have a selected node and you move your mouse to an existing node, it will basically connect to that node. It won't create a new node. So if I move my mouse down to this location, but if I right-click on this node when this is selected, it will put a pipe in and close the loop. So that's basically allows us to do to make any arrangement that we want with piping. Now, when you're laying out your system or after you've laid it out, if this node is actually going to be, say, a storage tank, if I select that node and go over here under the data, it will have a drop-down list of about 15 different types of nodes. And if I select tank, as shown over here, that will basically convert it into a tank and with all the properties of a storage tank, a maximum level, a minimum level, and all these different characteristics. So that's how we would complete our system. So that's all there is to it. Laying out your piping is basically a left click to select an existing node. A right click will draw a pipe from the existing selected node to the location of the mouse. And if that happens to be an existing node, it will close a loop. But if it doesn't, or add a parallel pipe. But if it doesn't, it will add a new node and a pipe. And then I select the node and use the drop-down list to change the node type. So with those steps, I can create any arrangement that I want. Now, there's some additional very simple operations that you can do. You can insert nodes, you can delete pipes and nodes, and you can move nodes around. These are just some additional, very simple steps that you may have to go through in order to correct your system or change your system. And the next couple slides show how we basically do that. To insert a node, you basically select a pipe exactly at the location you want to insert the node. So that if I want to insert, say, a valve at this point, shown right here where the arrow is, I would just go in and select the pipe at that point. It would become highlighted, turn red, which means it's selected. And then I would go to the insert key. This is insert key. It may not show up very well because it's a little small, but if you have your software open, you can see that. And then select the type of node. So suppose I drop down this list and select active valve. Then an active valve will be added at that location. Now, I know many of you have used different softwares and AutoCAD and so on, and you can appreciate this is a very simple process. If I want to put fire hydrants in here, I just have to select the location, drop down the list, and put a hydrant in. We have on-off valves that you can put anywhere, and they don't add nodes to your system, neither do hydrants, but the process of putting them in is very, very straightforward. You just, again, select the pipe at the location and drop down the list and add it. Now, you won't always, often you have to delete pipes and nodes because you've made a mistake or for some reason. And there's a delete key. If you select an item and you click on the delete key, it will delete that item. Now, there are some situations or some rules here. If it's an intermediate node like a fire hydrant or an on-off valve, it will just delete it because that has basically no major effect on the system. However, if it's an end node like a junction or a pump, it's going to have to delete all the pipes that are connecting. So it will ask you whether you really want to do that, and so you need to say yes and before you do that. When you do delete an intermediate node, it will change the alignment if that intermediate node is producing an alignment change in your pipe. So if I had a hydrant and when I reduce that, it's going to connect the two adjacent nodes together. So those are some things to keep in mind. If you want to move a node, it's very simple. You just basically left-click and just drag it. So you can zoom in and get very precise placement of the nodes if you wish to do that. So basically, I think with these set of rules, you can create a system very, very easily with the software. Now, when you get your software, your model developed, and say here's a model, then you have to input data for every node in the system and for every pipe in the system. And of course, each pipe has similar data. I mean, when we're going to look at this and just briefly in a little more detail. But each node has unique data. A pump has data that's certainly different from a storage tank or different from a valve. The pipe data, over the years we've found ways to really shortcut the effort required to put this data in. If you look at a pipe, you need a diameter, you need a length, you need a roughness for hydraulic calculations. You also would like to be able to identify the material and the rating of the pipe, just as additional information that's very necessary for proper design and so on, but not for hydraulics. But in any case, you can create a list of the types of pipes in your system. This list is like a ductile iron 6-inch with 150 rating, a PVC 6-inch with 150 rating, and so on. And if you do that, if you create those lists, and that's, it's very simple. It's a spreadsheet type list. Then when you're populating the data, you can just drop down your pipe type. For example, here I'll select PVC 8-inch, and it will populate all that data. So it's a very quick way of entering rather than clicking on a pipe and entering the diameter and entering the roughness and entering the length. Now, the length will be calculated if you when you lay out your model, and if you have a scaled background map, then that will be sufficient for getting the length, and you don't have to enter that data or calculate that data. Now, also, any pipe can have various fittings like elbows, T's, things like that. And again, over the years, we've created a way to shortcut this where you can bring up a list of the common fittings and just click as many as there are. This example shows two 90-degree elbows and a standard T. And it adds up the loss coefficients for those and enters that into the data. So again, you have a way to shortcut some of this data that can be quite tedious to get. You normally would have to go and look up the information and for all the fittings and add up the loss coefficients and enter this number, but we don't need to do that. Node data, this just shows a pump and a tank, and just the point here is just there's different data. For the pump, there's head flow data for the operation of the pump and the speed. We can handle variable speed pumps, so the speed is basically the ratio of the speed to the rated speed. So when this shows a ratio of 1, that means it's running at rated speed. If it was 0.9, it would be running at 90% of rated speed. And again, we're not trying to go through details, but just give you an overview. Tanks are devices where As they fill up to the maximum level, the altitude valve shuts. If it drains to the minimum level, there's an altitude valve that shuts. And these are used for extended period simulations. Very important for water distribution systems. You can turn labels on for looking at data. There's a label button up here that shows some of the key labels, and there's also a detailed menu where you can select any parameter that's available for a pipe or a node can be displayed. So here, if I wanted to display the pipe diameter and roughness, I could do that. Here's 8-inch pipe, 140 roughness, and check the data. And then that's something you would want to do when you create a model. You can analyze the model, do error checks, and run the analysis, look at a report, and the report would be a summary of the data, a summary of the results. Here's the data, the lengths, the diameters, the roughness coefficients, the results. Here we're showing flow rates and pressures. These are pressures, these are flow rates, and it's very easy to show different results. The pressure, the hydraulic grade line, the head, the flow in pipes, the velocity of the flow, things like that these are very easy to show graphically, and that's the ideal way to show results when you're using this type of software. So the point here was that it's quite easy to make a model, and to do the analysis and to look at the results. And as I say, we have demos, we have some audio, video tutorials, and some other presentations. And I would be surprised if any one of you could not, within just a short period of time, be able to create a model and do the hydraulics. Now, the second point I wanted to make today was that we have a lot of advanced capabilities for hydraulics, and our primary goal in the Pipe 2000 KYPipe Surge software is to provide a wide range of capabilities for doing the hydraulics. And so I want to show you just a few of the capabilities I'm talking about here, and this is sort of a list: pumps, hydro tanks, some what we call constraints for doing some direct calculations that are not normally done in this type of software, and a couple other things. So we're going to go through these just to give you an overview of some of the capabilities I think are pretty unique and will give the hydraulic and fluids engineer just that much extra capability to do the jobs he needs to do quickly. Now, in pump stations, that's obviously sizing pumps and dealing with parallel pumps and dealing with series pumps and dealing with variable speed pumps is a very important part of modeling. So I want to sort of cycle through some of these capabilities that we have here. To begin with, when you put pump data in, the recommended way to do it would be to put in a pump curve, head flow. And if you've done that, then you can very easily go to click on a button and produce the head flow curve. And you can also, when you put in head flow, you can put efficiency in. So we can plot these curves. So these are Pipe 2000 plots of a pump curve and the corresponding efficiency curve. This is just under facility management. We can create these curves for all the different pumps in the system. And you can also develop what's called a system curve very easily. Now, a system curve is basically a curve that will show you how much head you need to develop at the location of a pump in order to create or be able to pump a given amount of flow. In other words, it's flow versus head, and that's how much head you need to pump that much flow. And so we can very quickly create these. In other words, at any point in the system, just downstream of a pump, we close a pump and create this system curve. And this is what a system curve looks like. As your flow goes up, this is flow, and this is head. As the flow goes up, the amount of head required goes up. And where that intersects a pump curve is how much head or how much flow that particular pump will produce. So it's a very, it's very useful, and you can use this to select what pump you want. If I want to create this much flow, I need a pump that will intersect the system curve around this point. Now, one thing we've done, which I think is unique, is that we have at a single pump, you can have a drop-down list, and you can make that pump modeled up to 10 identical types of parallel pumps or series pumps. Now, that's a tremendous modeling advantage because it provides a very fast shortcut for modeling multiple pumps. So I can just take one pump here and say I'm running 5 parallel pumps, and it will do the hydraulics for 5 parallel pumps. So that can, instead of drawing in your model this and turning on all these pumps. Now this just shows the hydraulics. If I had 3 identical parallel pumps, each one would pump 1,500, a little over 1,500 gallons per minute. If I actually put in just one pump and say that there's 3 parallel pumps, I get basically within a fraction of a percent the same exact flow. So the hydraulics is the same, but the modeling requirements are much easier for using the Pipe 2000 capability for handling these multiple pumps. And on the plotting, you can go in and plot system curves versus multiple pumps. Now this is a system curve. This is 1 pump, 2 pumps in parallel, 3, 4, 5. And so you can immediately see with your system curve how this particular pump, if you have a bank of parallel pumps, how it's going to work. And the same thing with variable speed pumps. This is basically a system curve. Here's a variable speed pump operating at rated speed, 10% over, 20% over, 10% under, and 20% under. Now again, I'm just trying to give you an overview, and this is just showing that we have some very powerful capabilities to handle pumps and shortcut some of the modeling requirements that are normally required. This just goes on a little further. We're saying that if we wanted to have this pump 5 parallel pumps, it's telling us here, if we look at this curve very carefully, that you would get with 5 parallel pumps 970 gallons per minute at 161 feet of head. And that's what this curve will show you. So everything ties together as far as the pump curves go. I'm going to skip through some of this. You can actually put libraries of pumps in and go in and pull out these pumps out of your library. And the advantage of that, we're working with some pump manufacturers. We're working with Pentair pumps and Myers pumps and to create some of these libraries. So you'll be able to create your system curve and then go into the library and select different pumps and see how well they're going to work for your system. And finally, we can actually go in and put in a target for a pump. For example, we want a pump that will produce 500 gallons per minute and 140 feet ahead, intersects right here. And if we have a pump library, it will go through and select the pumps that best fit that. So if you had a pump library, you could come out very quickly with selecting the pump that would do the best job for you. Hydro tanks are sort of a sophisticated element. The hydro tank has air in it, and it's used to control the cycle of pumps. It maintains a pressure between a maximum and minimum value, and it automatically will turn on a pump if your pressure drops down to your minimum and pump it up until it reaches its maximum. Then the pump will come off, and the air pressure will provide the pressure required until you drop down below the minimum pressure again. So these are devices that are used widely for even in homes and in things like trailer parks where they have a pump providing pressure. They have a hydro tank to control the cycles of the pump, because if you are pumping into an area like, say, a trailer park, and there was no hydro tank, the pump would constantly be going on and off, and it would ruin the pump quickly. So hydro tanks are important elements for certain applications. They provide an alternative to overhead storage. There are systems here that instead of having a pump and an overhead storage, you have a pump and a hydro tank. I know around Houston, the Houston water system provides a lot of water supply to their MUD, or municipal utility districts, and they often have a hydro tank because it's a much less expensive alternative to an overhead storage tank. So, but the point here is that we can model these devices. There's some thermodynamics involved. There's controlling pumps, on-off switches, and so on. But we have an element, and you select the element and provide the data, and you've got your hydro tank model. When you have a hydro tank, for example, in a water distribution system, you have to be sure that the hydro tank can operate under a variety of conditions. And these next few slides, which I'm going through, just show how the hydro tank cycles, the pump cycle, for 24 hours of simulation. And this first one is sort of for a slack demand type of day. There's a normal demand type of day. And if you see a region like this is showing that the pump is on constantly, but it is maintaining pressures between 40 and 60. But if you went to a peak day, you might find something like this, where the pressure actually can't be maintained and might drop down to 35 psi. But again, the point here is not to learn about hydro tanks. It's just to point out the fact that we have the capability of modeling these devices in a very straightforward fashion. There's also a sort of a new development, a holding tank. These are very widely used for, say, sewage collection. And what this is a combination tank and pump, where if the tank is being fed, say, sewage effluent, and when the water or the level gets up to the high level, the pump comes on and automatically pumps it down to the low level. And so we have this device that you can model that incorporates all these characteristics: a tank, high level, low level, a pump, controls are all incorporated in this element. This, for example, if you had 3 of these holding tanks and you were pumping to a reservoir here and you ran a couple hours of simulation, this would show how rapidly the pump would cycle. For example, this one has perhaps a higher rate of effluent, so it's cycling every 0.4 of an hour, where this one is cycling about every hour. But again, the point is, this is a fairly complicated device, and with our desire to handle these devices that are needed by the hydraulic engineer, we have a device for a holding tank. There's also a capability we have here that's unique, and that is what we call direct determination of a design or operation parameter. And I think you can see how this works, because when you set this up, it's called a constraint, but it's actually a result of several years of research we did at the University of Kentucky, where we added capability to the hydraulics of piping systems. And so what we can do here is to maintain a pressure or a head of a certain amount at a certain junction. We can calculate any one of these parameters, and if you didn't have this capability, you would have to do this by trial and error. I think the next slide would show this a little bit better. Suppose I wanted to maintain 65 psi out at this node, and I had a variable speed pump. So if I wanted to, I've just set this up. I want to maintain a pressure of 65 at this node, which is node number 20. I calculate the pump speed for this pump, and it could be a group of pumps or a single pump. And when I do that and run the analysis, I get the pressure of 65, and it tells me the pump has to run at 1.426 times rated speed. So, I mean, that has happened directly. The only way I could do that normally would be just to increase the pump speed and see what the pressure is, and increase the pump speed and see what the pressure is. So this is another capability a unique capability that we have. And a third one here would be what we call a pressure supply. Often, as engineers, you need to do a hydraulic analysis, say, of a subdivision, and you don't have the hydraulics model of the entire distribution system. So, or you're doing a hydraulic analysis of a sprinkler system that connects to the distribution system. So we have what we call a pressure supply that basically will model the capability of the distribution system to supply the subdivision or the building, whatever you're looking at. And the way we normally do this, suppose we had a building here and we needed to put a fire protection system in, we would run a flow test of the nearest hydrant and get the static pressure and the residual pressure and the residual flow. Now with that, the NFPA and the AWWA say that, well, this is how this will work. In other words, this is a line, and it's showing you here's the static pressure with no flow, and here is a test point. And you draw a straight line on a logarithmic scale because it's to the 1.85 power, so the Hayes and Williams equations applies. Again, that's not too important, but that's what our pressure supply element does. If you pull off 500 gallons per minute, the pressure will be down here. If you pull off 1,000, the pressure's here. And so it allows you, with this pressure supply, to model a fire sprinkler system, a subdivision system, accurately without going to or without needing a model of the entire distribution system, which you would seldom have access to. I think I'm sort of running out of time. I want to go quickly over surge analysis. This page here sort of shows you basically, or talks about why we need a surge analysis. Now, surge analysis, we're talking about startup and shutdown primarily. Pressure extremes almost always occur during a period of transient flow. When you start up the system or you shut down the system, you get the highest and lowest pressures. They may exceed the design limits. You may get unacceptable low pressures. Low pressure transients can cause health risks. When you trip a pump, you get low pressures in your system, and that can very easily lead to intrusion of pathogens into your system. So these cartoon type slides, and you have access to the slides, so if I have to go through them a little quickly, you can look back at them. But this just shows this is probably the worst condition. A pump is pumping, basically providing energy, pushing water up an incline, and the pump fails. What happens here is the water tends to want to keep going, and we simulate this with an engine and freight cars. But you can actually get separation. Gravity will take over, and the water column will come back and can cause great damage. So you don't want this to happen. When you start up a pump, you can create pressures that are much higher than the normal operating pressures. And anytime you shut down, a check valve shuts or a valve is shut, it's going to compress the flow and cause high pressure. So valve shutoffs are conditions you need to be concerned about. Well, here's an example of a surge analysis. We're going to basically shut this pump down quickly. And the next slide sort of shows with the pump operating, the pressure here is about 54. When it's not operating, it's about 50. So there's really very little pressure change between the pump being on and off. But if somehow you had a power failure and you couldn't control the pump shutdown, this is sort of the type of transient you would get. You would get high pressures over 90 psi, low pressures down to 30. In fact, in part of the system, all these highlighted locations, pressures had dropped down below atmospheric, which means in a drinking water system, you could be intruding pathogens because you suck in dirty water, and that's a no-no. So we can't really allow this pump trip. We need to do something about it because it will jeopardize the health of the people using the distribution system. Now, if you put a tank in there, a surge tank, when the pump trips, the surge tank is pressurized and can provide water to the system. And just quickly, this is what the pressure trace would look like, but here's a comparison. So the point here is that you need to be able to do surge analysis, and we have, of course, in the Pipe 2000, Surge 2000 software, we have a very tight capability to run surge analysis using the same models with very, very little additional effort. You can create your surge analysis. And then the last thing I want to show you is that we've created some pretty impressive graphics to show folks. And what we're going to do is look at, here's a system where, let me look at the next slide. You're going to trip this pump, and you're pumping up to an elevated tank. When you trip the pump, you're going to get low pressures going up the system. And we can look at the tripping the pump with no surge protection or tripping the pump with some surge. Okay, so here is a new graphical tool we have. We have a pump running here. We have a check valve. We're going to trip this pump. This is the hydraulic grade line. Now, when you trip the pump, the pressure is up here around a couple hundred psi. It's going to start dropping, and you'll see what happens when you trip this pump. The hydraulic grade line will start dropping down. I don't think I got it, but I'm going to get it here. Okay. Now it starts dropping down. The check valve shuts, and this indicates cavitation. There's a wave going down the system, and the pressure is dropped to the point that the flow cavitates, and that's a very bad situation, especially for a drinking water system. These cavities collapse, and they cause pressure spikes, and you just don't have a good situation. So when this pump tripped and the valve shut, we got into a situation which wasn't really acceptable. Now here's some air valves. What happens now is when the low pressure comes here, it sucks air in, and the pressure then won't go down all the way to cavitation, and that's the idea here. So take a look at this one. Now again, you get the same thing, check valve shut. Now you see as you're going down here, you don't see that cavitation, but something does happen here that's fairly bad. If you look at the air here, it's going to be expelled, and when it's expelled, there's a big pressure slam. It's called an air slam, and once that happens, you start getting cavitation. So this particular type of air valve, a nominal type air valve, maybe a 2-inch opening, it controlled the initial down surge, but it didn't control later down surges. Well, finally, if you had, say, a surge tank here, now the difference here is when the surge pressure goes down, the surge tank can provide water. So let's see what this does. Pressure drops, but you can see the water level is dropping a little bit, but the pressure never drops down. It stays up well above the positive values, and that's a very good situation. And so anyhow, the point here is that there are tools, too, to help you explain to clients and so on exactly what's happening with your various tools here. Let me get rid of these things. Okay. All right. So we're basically, it says here, download the demo, and we provide support. Let's see, the last one is the support, telling who's providing support. Jana talked to you earlier. She's a support engineer. Bill's a support engineer. Both Dr. Lingretti and myself provide support. Doug is our programmer. So hopefully you have all the tools you need, and I'm probably over my allotted time, so I'm stopped.
Well, we can field some questions here. We have a couple in the meeting chat, and if anybody would like to throw some more questions into the meeting chat while we're answering these, then feel free. Dr. Wood, the first question is, and you might want to share your screen, how do you
share my screen? Okay.
Yeah, sure. Do you have Pipe 2000 open, the program open?
I do.
Okay. How do you upload a map or image into the background? Can you show
Okay, wait, now I don't know if I got my screen shared. Let's see, screen share. Okay. Now I'm sharing my screen, right?
Yes.
Is that what it says?
Yes,
is it showing
can see
it
it
now? Okay. Well, under map settings and backgrounds, I've got this drawing on. I can make this basically hidden, and now if I go back, I will have no background. So that's how you do it. You basically go to map settings and add a map. I go to a browser. Here's a browser, and I can add any map that I have that's appropriate. Now, I don't have other appropriate map for this particular, but you can also put in, as I mentioned earlier, grids. I could turn on a 1,000-foot grid line and go back to the map. And here's your grid lines. So hopefully that'll help. There are some audio, video tutorials on adding maps and so on that you can download and you can look at.
Okay. And I'd like to interject if you would click on the map settings background tab again.
Okay.
If you have a DXF, it's best to use the section at the bottom. There's a button that says Load CAD File, and it will bring up the browser just like the other one. And another thing, once you have your map added, it's always a good idea to use the zoom to map commands, because sometimes it'll be in a coordinate set that isn't where your map is centered on. And so it might seem like the map hasn't been added, but in fact it's just at another coordinate location. So if you use the zoom to selected map or zoom to CAD file buttons, that will help you find your added map. Okay, the next question is, when we were doing the system head curve analysis, the data you had shown indicated that there was an available head of 5. And what does that mean?
Okay. I can do that with this system. I'll turn these labels off. Here, when you have head available on the suction side, here's basically a reservoir with 5 feet of head. It's got a grade of 610 and an elevation of 605. So, and if there was a short suction line with very small losses, then I would say that, or this pump might connect almost directly to the reservoir. There would be an available head of 5. So that's what you must take into account how much head is available on the suction side of your pump in order to properly represent the system curve, because the pump only has to put in the head that's not available, so it already has, say, 5 feet of head from the suction. I hope that covers that.
Okay. The next question is, how do you insert a variable speed pump? Or I guess define one in this case.
Well, basically, here's a pump. It's got a head flow curve, and it's got a speed ratio. It's a variable speed pump. If I run this analysis, and I look at the flow rate, let me look at the flow rate here. It says there's 1,102 gallons per minute. Now, if I go to that pump and put that pump at 1.1, now it's operating at 10% above rated speed. So when I do this analysis, I'm going to expect an increase in flow rate. So we have, I mean, the variable speed pumps are there. They just primarily, see, this has gone up by several hundred feet per second, or several hundred gallons per minute has gone up. So basically, a pump that's described by head flow data is automatically a variable speed pump. If it's not going to work as a variable speed pump, you just leave the speed ratio at 1.
Okay. On the pump curve graph and the system curve graph, you indicated a target point. Can you insert this target point, or how do you do that?
You can. I'm going under facility management, the pump system curves. I don't have a system curve, but here's my pump curve. But if you go to select down here, now you have to have a series of pumps in here. We actually have a bunch of pumps, but I think these are actually not well defined for this. But if you go here to select, it will ask you what head and what flow you want, and then it will select a pump that comes the closest to that of the ones you have in there. Now you have to have a pump library in there, and I don't have one in this particular example. But that's where it comes from. It comes under facility management, pump system curves, and then under select here, specify a head and flow closest to them, and the matching pumps will be displayed.
Okay. Can you update the pump library yourself?
Yes. You can under other data here. There's library data, and these are backflow preventers. I don't know. I don't have a pump library in here right now, but as I say, we're working with some of our manufacturers, or some pump manufacturers, to create these libraries. You could create your own. You can either clear out the default data that's in there, or you can scroll down to the bottom of the table and just start adding data to the data that's existing, and it'll appear when you go to select the pump library pump. But again, that's something we can help you with, and we do that all the time. So, but the point is, you can create your own libraries quite easily. Yes.
Okay. The next question is: are pump controls available in Surge?
Well, I guess the answer to that is in Surge, when at any time you can say change the speed of a pump. So I'm not sure that's okay. That's number one. So it's not like you basically turn the pump on when the flow goes down to a certain point. However, let me back up a little bit, because we just completed the development of control valves, and the control valves will control pump speed. You can control the pump speed to maintain a pressure at a certain point, or to maintain a flow at a certain point. Now that'll be a 2012 feature, but it has been developed. That we were working with FM Global Company, which does all the fire sprinkler testing, and we developed PID control valves and just simple control valves that will control pressure and flow either through a valve or through pump speed. So I guess the answer is, at this point, I don't think we have the controls you're talking about, but we will within the next few months.
Okay. I guess the question is, it says to scale map. I suppose that's how to scale a map, or
Yeah. Okay. I mean, there's a lot of there's some different ways to scale maps, and I was going to turn this map back on. So here's a background map. Now, if it's AutoCAD or something, this is a DXF file. It's probably already scaled. But you can go in and basically find the length, say, from, say, this point to this point. You can lay out a pipe and see what the length is, and you can then put in a scale factor. All these things have scale factors. Here's a scale factor right here for the for the map. Since it's an AutoCAD map, there's no scale. But if I put in a scale factor, it will modify the scale of the background. So generally, you go in there and you lay out a pipe or an indicator along a known distance, and you compare that to the distance that the program is giving you, and you create a scale factor from that. And again, we have audio, video tutorials and help on that, but the answer is yes, you can do that, and it's a fairly straightforward process.
Okay. How do you change a pump from pumping into the system to make it pumping out of a system?
Okay. That's fairly easy. You see, pump is a directional element. We have regulators, we have pumps, and here's when you pull up the data for a directional element, you'll see this arrow. And if I click on that arrow, you'll see the direction changing. So that's how you change it. So now if I rerun this analysis this way, it's going to be pumping out of the system. Might not like it very well, but now it's pumping several 1,000 gallons out because it's got elevated storage in there. But you can see the direction is changed. So hopefully that answers that question. That's all there is to it, just that direction. That'll show for a number of elements. Yeah.
Okay. Does the software address both compressible and incompressible fluids, say crude oil and natural gas pipeline system?
Separately?
So I guess,
separately.
Well, I guess. Yeah, I would think that would be separately.
Yeah, we don't handle two-phase flow, but we have an engine to do compressible flow. We do natural gas. We do methane collection systems. I mean, our users do, and so one of the if you look here, one of our modules is a gas engine, and there's another one for steam. So that it does that for steady state flow, and it can be an ideal gas or a real gas where we put in additional data. Okay,
that was the last question.
Okay, so, well, we're a little over time, so...
No, I think there's one more.
Okay.
Okay. I don't see it. Do you want to relay it?
Yeah, let me send it again. One second.
Okay.
Well, as we said all along, you're certainly welcome to call our support people. That's one thing I think we are very, very high on is the way we handle support. We support you if you're learning the program, if you bought the program, and there's no cost to it. So I don't think you'll find that with us, our competitors. So.
Okay, I got the last question.
Okay,
I'm sorry, Dad. Don, the program, can it perform a probability analysis for a number of pumps running? This is for a pressure sewer system with a prescribed daily volume per household.
We can handle these low pressure sewer systems and hundreds of pumps. We don't have a technique built in at this point for doing the probability analysis. We can just turn on various, 10 or 12 pumps and run the analysis. We have basically an element for low pressure sewer systems, which turns on, which basically has a pump and a tank, and when the tank fills up, the pump drains it out, and so on. But I think probably the answer is no, we don't have the probability tool built in. We have been talking about that. And we'd certainly welcome any suggestions as to what, there's not a real consensus on how this should be done. So that's why I'm saying that we welcome any suggestions as to how you would like to see this done. Okay.
Okay. That's the last question, and we want to thank everyone for joining us, and please look for future webcasts, and as Lisa indicates in the chat box, if anyone has any topics that they'd like to have covered in the future, we welcome suggestions. And thank you, Dr. Wood, for presenting today.
Thanks, everybody, and we'll be available to talk to you if we have the opportunity. Bye-bye.
Thank you all for coming.